Rack is still the same, probably. One button. Yeah.
Is it just 2 lines?
Detection of data transmitted. So just to review what we talked about last time, we showed how to modulate a signal, and we also showed how to detect it in the absence of noise. So remember what's going on in the detector. We have our sampled observation y of k. We pass them through a linear time invariant filter. Impulse response h of k. And then we make a decision. And our idea with the decision is that it implements a function dz of x, whatever is input to the decision. Actually, let me say yk, the output of the filter we said was phi of k. And we evaluate this every NB samples. So dz of phi, let's say the first filter output phi NB, excuse me, phi j NB, the JF filter output, is equal to 0 if phi j and b is greater than z, and 1 if phi j and b is less than z. So there's your decision function. So where we were last time, we were starting to talk about noise. So we said y of k is equal to some scaling factor times the signal we sent, S of k, plus the noise, N of k. So what we need to know about the noise in order to evaluate how decisions are made, we need to know its mean. We need to know its variance. And we need to know its autocorrelation. Last time we argued this is zero mean noise, so actually all of these properties, we need them at the output of the filter. So the mean of this process is 0, we need the variance and the autocorrelation at the output of the filter. So let's remember, for additive white Gaussian noise, for an additive white Gaussian noise processing continuous time n of t, the autocorrelation is equal to the delta function with coefficient n0 over 2. That means when you take the Fourier transform of the autocorrelation, you get the power spectral density. We talked about that last time, and in this case, it's Sn of j omega is equal to n0 over 2. So notice that's not a function of omega; it's constant for all values of omega. So every frequency component has the same value of noise. So from the hardware model, before we sample at the receiver, so remember the receiver looks like this. We have physical layer access here. We then have amplification. excuse me. I suppose it depends on your perspective here, but we have noise introduced, then we amplify, and then we do a low pass filter before analog to digital conversion, and then we do the rest of our tasks. So this is all the continuous time stuff on the left here.
What's that? DCA?
What?
Okay,
And on this side is discrete time. So generally I've said we can ignore everything in continuous time, but what we do need to pay attention to is this low pass filter. This low pass filter, its only job is to prevent aliasing. So in other words, it's going to cut off components of the noise process that might lead to aliasing. This is defined for all frequencies, and in order to take a proper sample, a proper set of samples, we need to low pass filter and cut it off at the Nyquist frequencies. So, the low pass filter, I'm going to assume this is an ideal low pass filter with cutoff at the Nyquist frequency. The Nyquist frequency, you should remember from signals and systems, is the highest frequency that can be properly represented by sampling. And what is that with respect to the sampling frequency?
Twice sampling.
It's half the sampling.
Sorry, half the
Yeah, the sampling frequency is twice the highest frequency. The sampling frequency is twice the Nyquist frequency. So this is half the sampling frequency. So in other words, in the frequency domain, this low pass filter, let's say it has in a frequency domain transfer function HLP of j omega. That's HLP j omega is equal to 1 for all the pass frequencies. That's if omega okay, let's just take a quick aside here. Sampling frequency Fs is 1 over Ts. Half the sampling frequency is 1 over 2 Ts. But we're talking about omega here, angular frequency instead of normal frequency. So I need to multiply Fs by 2 pi. So omega S, this cutoff is at this regular frequency. In order to get that into angular frequency, I multiply by 2 pi, so I get 2 pi over 2 Ts, which is pi over Ts. So in other words, this low pass filter passes everything, ideally passes every frequency less than pi over Ts, and rejects everything larger.